is calling me. It speaks both day and night. It's full of dark and light.
Hello and welcome to SkyTour Radio here on KGRAradio.com. I'm your host, Mark D'Antonio, here with my astonishing co-host, Amanda Curran. Hello, Amanda.
Hi, Mark. Hey, all.
And we want to welcome our KGRA listeners, the best audience on the planet, to the broadcast. Just a few announcements. I'd like to encourage you to subscribe to the companion stream to SkyTour Radio, which is SkyTour Livestream, and that's on YouTube. And that's where we take you on clear night journeys with our high-end observatory telescope, ultra-sensitive cameras. It's all live and it's all real time. Now, Amanda's done this with us, obviously, for a long time, and she's had a great time, and she's learned an awful lot, haven't you?
Oh, my God. And even if you don't know anything about it, the images are so beautiful. I really encourage you all to check it out.
Cool. And I agree with her, and not because it's my thing, but just because this is a great way to outreach. So, you see the universe as never before on SkyTour Livestream. So the journeys are going to resume in just a few short weeks, and we will be waiting there for you. Don't forget to click the bell and get notified of our events. Lastly, last announcement before we get going tonight is please visit the store at fxmodels.com. That's fxmodels.com, or at the FX Models Planetary Replicas page on Facebook. There you can purchase Moon, Mars, and Pluto swag in the form of 3D printed craters that are just accurate and very, very cool. Now, our KGRA listeners, if you enter the code ST15, that's Sierra Tango 15, ST15, during checkout, you will get a $15 discount. Now, the links to these stores are on the SkyTour Radio page at kgraradio.com. And I look forward to seeing you there and talking to you. So tonight on SkyTour Radio, Amanda, we're going to do something really cool. We're going to talk about some of these new planetary systems that have been brought to us via the Kepler and K2 mission. Now, K2 is the continuing mission of the Kepler Space Telescope. All right. And when the engineers actually figured out a way to fix the Kepler Space Telescope, they actually managed to create a way for the K2, for K2 to come to life. And K2 was actually something that came about because the engineers managed to stabilize the Kepler Space Telescope, which lost its stability capability. Ooh, that's an interesting way. Stability capability. Well, anyway, so we're going to talk about those, and we're also going to look at what are the prospects for alien life on some of these planets, and what might the alien life look like in these places? So we're going to actually go down the speculative path tonight, and it's going to be a lot of fun. And it's all tonight on SkyTour Radio. So let's jump right in. Our first system that we're going to talk about tonight is one called Kepler 90. Kepler 90 is 2,500 light years away. That's 2,500 light years. Now, that's really far away. But there have been 8 planets found. And now some of the diagrams online show 7, but it's actually 8. Okay, and these 8 planets are circling a star that's a star very much like our sun. It's a G-type star. If you remember the letter nomenclature for stars from hottest to coolest, it's OBAFGKM. Well, all right, the star is a G-type star, and it's a little bit hotter than our sun. And all the planets around that star are closer to the star than our Earth is to the sun. So the habitable zone, the place that's not too hot, not too cold, what we call the Goldilocks zone for our star, is 1 astronomical unit, which is 93 million miles from our sun. All right. And the habitable zone for this star, Kepler 90, is not 1 astronomical unit, but 1.37 astronomical units. Okay, that's the beginning of the zone, and it goes out to 2.3. Now, you have to think about and say, well, that means that in that system, Mars would be probably the habitable and quite comfortable planet. Mars is 1.5 astronomical units from our sun. All right. And the habitable zone for Kepler-90, where you can live happily and have liquid water on the surface if you have enough atmosphere, is 1.37 to 2.3 astronomical units. So it'd be right there. It'd be pretty good. So Mars would be the quote unquote Earth in that system. But there is no planet there that we know yet of that nature. But there is the outer planet, the planet that's farthest away from the star. All right. This one is fairly big. All right. And there's 7 of them. The 7 planets, besides there's 8, but the farthest one is called H, little h. And the nomenclature is the closest one is B. All right. And then the next one is C, then D, E, F, G, H, I, etc. Well, this one is H, okay? And B through G are all well inside the habitable zone, and not inside the habitable zone, but outside the habitable zone, closer to the star. And then the habitable zone starts, and then H is right there. So it might be like the planet Venus in our solar system, all right? But it's pretty interesting because those 7 planets that are in front of it are closer to the star, and then H is the one that might actually have something that we might be interested in. Might be alien life there of some kind. Now that's kind of cool, but they're right on that inner edge of the habitable zone. So it's going to be a hot planet for sure. And at its size, I calculated the surface gravity for this planet, right? This planet has a surface gravity that's it's actually 2.9 times the gravity of the Earth. So that's pretty substantially more. Now that means that the acceleration due to gravity is 29 meters per second squared, okay? Now what does that mean? It means if you drop a rock from any height on that planet, it will fall at a rate of 29 meters per second every second, all right? So it'll go faster and faster and faster. That's what we call an acceleration. And we characterize the gravity of planets with a, quote, acceleration due to gravity. Now, how does that 29.1 meters per second squared, that's 29 meters per second, how does that relate to Earth? Earth is 9.8 meters per second squared. All right, so now we can take that, make a ratio, and figure out that that planet has a gravity that's almost 3 times the Earth's. So you'd actually have a lot of trouble walking on that planet. Okay, why? Well, how much do you weigh? Add 2 of you on top of you, right up over the top of your head. All right, and try and walk. You can quickly see that until your muscles get a lot stronger, you are not going to walk. All right, so that's kind of interesting. Okay, and so there's 2 trains of thought about what this planet may be. Okay. This planet might be a gas giant, and that's actually the most likely scenario right now. But because of the possibilities and because of the questions we have with our own Venus in our solar system, we're wondering if maybe there aren't some type of floaters, that is floating life, in the upper atmosphere of this planet. Now, there's nothing that's telling us that they're there, and there's nothing in the chemical composition of the atmosphere can tell us anything yet, because we can't see that yet. We may have adapted. I mean, hydrogen is probably what the atmosphere, and hydrogen is very buoyant anywhere in the universe. So if that's the case, then perhaps they have gas bags, hydrogen gas bags. Not so far-fetched. The Portuguese man of war in our own oceans uses an air-filled bladder to float on the surface. So life does use flotation, even on our planet. So I'm not speaking so totally hypothetically, all right? Based on science, this is possible. So now, any creatures there with a high atmosphere life form, it would still have access to the sunlight, right? And there's lower temperatures up in the upper atmosphere, even though the planet is closer to that star. The temperatures will be lower in the upper atmosphere than they are on the surface. All right. And then they have access to hydrogen gas for possible flotation. So that's kind of cool. Now, those are advantages. Now, what are the disadvantages? Well, there's no known life form that exists exactly that way on Earth. We don't have floaters in our high altitude, right? Not other than bacteria that get airborne, kind of a thing. But we don't have true upper level, higher life forms in the atmosphere like this permanently. But they have higher ultraviolet exposure. That is, the ultraviolet energy that comes from the star is going to be more significant than our own. So they will be, pestered by that a lot more than, they might otherwise be. But they could develop protection from that. All right. But on top of that, they will also be in more danger from solar flares, or that is intermittent radiation being expelled from the star in copious amounts. Here on Earth, we call those CMEs, coronal mass ejections, and they're responsible for killing satellites or damaging them, power outages, and more here on the planet. So they cause damage anyway. So there's no reason why we wouldn't expect that they would do that there. So those two things could thwart high altitude life, possibly. And we know the temperature would still be a little hotter than Venus. But we do know that if there are creatures up there, they're going to have developed, most likely, they're going to have developed some type of vision. Now, every life form on this planet has developed some form of vision. All right. And there's other life forms that have developed, advanced life forms. And there's some life forms here that have actually developed supplements to their vision, like bats. They can see, but they can also ping. All right. Same thing with some of the fish in the sea. All right. And whales have different ways of detecting things. All right. And so I think it's important to understand that life forms don't have just one way to detect their environment. And we'll see that that's possible. We're actually somewhat limited. We don't have sonar. We just have vision. And we actually can see in a very narrow range of the visible light. That, for us, bipedal hominids that walk on this planet, was selected as the most successful life form, of course, after the dinosaurs died out. Interesting stuff, Now, if the planet isn't a gas giant and it's a rocky planet, then there's a couple of prerequisites that may exist, and we have to consider this. All right, these planets will be, or this planet will have to have an atmosphere that's thick enough to block any ultraviolet or UV radiation, or the creatures on the ground would have to develop some type of protection and actually become sort of immune to the ultraviolet effects. Here on Earth, ultraviolet energy can strike us and give us skin cancers and other things like that. So in this case, if they have an atmosphere on Kepler 90, for this particular planet, then Kepler 90H, then what we would have to expect is that the atmosphere would have to be very, very dense. That is to say, dense enough so that a ultraviolet shield could develop. But the problem with that is there's more going on there, right? We look at the pressure from our atmosphere. Our atmosphere presses down on you. Every square inch of your body is hit with 14.7 pounds. Every square inch. And that's the direct result of the weight of the atmosphere that's over your head. All right? Has nothing to do with anything but the weight, which is, of course, the mass of all the atoms over your head times the acceleration due to gravity. That's the mass times that 9.8 meters per second squared of the Earth I told you about. That's called mg, mass times g, the acceleration due to gravity. And that's 14.7 pounds per square inch here on Earth. Now, life evolving under a higher pressure will have to specialize for that environment. As you know, if you climb a mountain, your ears pop. Well, if you go to space, your body not pops, but you're finished. Okay, you can't survive. But I would say, if you look at the deep ocean, life there exists in a very limited range, and they're under intense pressure, right?
Your ears pop there too.
What?
Your ears pop there too.
Yeah, the other way.
If you go under deep enough, yeah.
That's right. So, see, we have a limited range, and so life forms have a limited range. That's the whole point. We can't take a life form that's on a planet like that and just bring it here and expect it to answer our questions. Because if it's under more atmosphere, it's going to be under higher pressure. And if it's under less atmosphere, it might be under less pressure, and if it doesn't breathe oxygen the same way we do, it could sear any lungs it may have with too much oxygen or not have enough. See, there's so many things. So that's the whole point. Now, if that planet is rocky and has an atmosphere, then we know that the atmosphere, in order for the atmosphere to be integral and be permanent around that planet as best it can be, the planet also has to have a magnetic field. Now, our magnetic field is the reason that we see the auroras, the northern lights, because high energy charged particles come from the sun, and these are really, really high energy particles that could actually attack the molecules in our atmosphere, like water vapor, H2O, with 2 hydrogens and an oxygen, and split them apart. Over time, the water on our planet would end up being lost to space, and that's a problem. But the magnetic field, you see, causes these particles to get trapped in this magnetic field because they interact with it. And those that make it out of the magnetic field spiral down on the poles. And when they spiral down, they interact with the molecules there and cause the northern lights. That's what the green shimmering is. And if you've ever seen the northern lights, they're amazing. They actually scream across the sky in very, very high speed, it seems to you, when you look at it. And it's just the most amazing sight. But if UV levels are higher around that star, around that planet from that star, then you need better protection, right? And we know that you need oxygen for life as we understand it. And we know that here on Earth, a successful template that started up here on this planet is photosynthesis, that is converting sunlight to energy. So as long as the sunlight can reach the ground, then maybe plants form there. See, and any plants, though, would probably need better UV protection if the atmosphere is like the Earth's, because it would be sort of a thin shell, because our atmosphere is not actually very thick, all right? But either way, life there is going to be an extremophile. That is an extreme form of life, and that's something that, we would have to deal with. We'd have to say, wow, an extremophile is like, the bacteria that we find in the hot springs where we could never live, or the creatures that live around the black smoker sulfide chimneys in the deep ocean, 2,500 meters down in the Pacific on the Juan de Fuca Ridge. Okay. And this life hides in the shadows. Okay. So, could there be intelligent life forms on Kepler-90? Well, maybe not. Okay. But we don't know. See, now James Webb will tell us. It'll tell us whether there's any kind of atmospheric components, any kind of composition that indicates that life is utilizing the atmosphere. Maybe there might be some methane. There might be water vapor. There might be some CO2. There might be industrial pollutants if it's actually a colonized planet or a planet that has advanced life on it. So we don't know, but it'll be fun to find out, and we'll find some of that out next year because Kepler-90 will be a target for James Webb. Now, moving on to the next star system. I don't know if you had any questions, Amanda. We might want to get to them now before we move on.
We do. Well, a break's coming up shortly, so we may as well get some questions on Kepler-90. Yeah. There was a good one, and I think I might actually be able to answer it, but
I want to hear this. Yeah,
you're here on standby just in case I lead them astray.
We have 2 minutes, but go ahead.
Okay. Kathy asks, what happened to Kepler-90A? Because you were talking about B, C, D, and on.
Very good H. question. Very good question. Is that the one you think you know the answer to?
I think so. Is it because Kepler-90 is the star?
Right. That's that. You're getting. You're getting. I hate to say it this way. You're getting warm. That's getting warm. But yeah, Kepler-90 is the star, and so we end up.
So there is no A.
Right. We don't use a little a for this. We just say it goes from B outward. It's a nomenclature.
Is that the same as Alpha Centauri?
And no.
Proxima?
Well, no,
Proxima
because
B?
No. Well, it's the same nomenclature for the planet, yes, but for the star systems, and we're going to talk about another triple star system actually as part of this in a little while. So we'll just keep we'll keep that in our back pocket for now. But the fact is, the stars have their own nomenclature, and the planets have their own. The planets start with the letter B. Kathy, that's a great question, and I'm glad you asked.
That's a question.
Yeah. So I think that I think that that's something that we have to consider too, is that, we're going to end up having a lot of nomenclature to understand as well. And I don't want to make it sound like, we don't, but that'll happen. We're going to end up with a number of new techniques and new stuff that we're going to be talking about, because these are exoplanets. This is a new science, folks. And, I'm here to cover it for you and to put it in terms you can understand, because frankly, who else will? All right. I mean, there might be some, but you know what? We'll talk about this after the break, but I just want to let you know that we're all going to be here for you at the other side of the break, and we'll be right back after these words.
This is SkyTour News for February 25th. I'm Amanda Curran. Today, in 1958, the Minuteman program was started. With operational drawbacks of the first-generation liquid propellant Atlas and Titan ICBMs apparent, a series of development motors of increasing size and performance made the solid propellant ICBM feasible. New miniaturized inertial navigation systems and small nuclear warheads meant that the Minutemen would have a fraction of the cost, weight, and silo size of the Atlas and Titan missiles it would replace. The perceived but non-existent missile gap with the Soviet Union and the vulnerability of the Atlas missiles made Minuteman the highest national priority. 1,000 silos were built across the United States in one of the largest construction projects in history. Today in 1969, Mariner 6 is launched. 10 days before the scheduled launch, a faulty switch opened in the main valves on the Atlas stage, releasing the pressure which supported the structure, and as the booster deflated, it began to crumble. 2 ground crewmen, who acted at great risk of the 12-story rocket collapsing on them, started pressurizing pumps, saving the structure from further collapse. Mariner 6 launched on time and went on to return 49 far encounters and 26 near-encounter images of Mars, and was able to measure UV and IR emissions, as well as radio refractivity of the Martian atmosphere, and was able to provide radio science, the information needed to refine estimates of the mass, radius, and shape of Mars. On February 26, 1982, WestStar 4 was launched. WestStar was a fleet of geosynchronous communication satellites, totaling 7 in all, and were first launched by Western Union and NASA for domestic and commercial use in sending internal communications, such as telegrams and mailgrams, to Western Union bureaus and U.S. post offices respectively. It was also utilized by outside customers, using it for sending television and radio programming via satellite to their local affiliate stations throughout the 1970s and 80s. The later WestStar 4 and WestStar 5, launched on June 9, 1982, were based on the Hughes HS-376 platform from the Hughes Aircraft Company and had 24 transponders available as opposed to the 12 on WestStar 1, 2, and 3. Hughes later launched the Galaxy 4 satellites in 1992 and the Galaxy 5 in 1993 to replace WestStar 4 and 5 respectively after the latter satellites reached the end of their useful life. This is SkyTour News. I'm Amanda Curran.
Hey, hello, and welcome back to SkyTour Radio. This is Mark D'Antonio with Amanda Curran, my co-host, and we left off with Kepler 90, this now famous exoplanet that we found, and we have a couple more to go through, a few more, just 2 or 3 more. Again, if you have questions, send them up into the chat. We'll try and grab them. One of the things I wanted to get to is one of the questions that actually came in during the break. Charles asked if Kepler found any satellites around these exoplanets. That's a brilliant question, Charles, and here's why. Let's actually consider Kepler 90H. If Kepler 90H actually has a moon, which we cannot see, we can't tell if these planets actually have moons. But if it had a moon, then that would mean more to us for the advantages of life forming there. Right now, H is the outermost planet in this and around the star system, and probably the most massive. But that could also be a detriment for it, because it would also attract most of the impacts from asteroids in that system and dust and debris in that system. But if it had a moon, that moon might do that, and that moon would also, if there was water on a rocky version of this planet, the moon would cause tides, and the tides would cause tidal pools. The tidal pools would lead to life like us, potentially, if that is air-breathing mammals as opposed to water-based creatures. But that's just a thought. That's a good question. Very, very good question. But we can't see any satellites, any moons, that is, around any of these exoplanets at this point. And moving on, we're going to Kepler 80. Now, Kepler 80 is 1,100 light years away, 1,100 light years away. And it's an interesting exoplanet because, it's an interesting star because it has 6 planets. But just like TRAPPIST-1 that we talked about last time, not last hour, last segment, but last show, Kepler 80 has 6 planets, but they're all closer to the star than Mercury is to our star, right? And so it's kind of like that. Now, we didn't know there were any planets closer to the star than Mercury is to our sun, and because, again, it's 1,100 light years away. If you can just imagine the feat of trying to see transit data, that is the data of a star slightly dimming because this little tiny pinprick goes in front of it, then you understand what we're up against. Okay, now this means that we had to use different techniques, and so the way we found these planets, all 6 of them that are closer to the star than Mercury is to our sun, is through something called machine learning. It was an AI, an artificial intelligence, that made this find possible from 1,100 light years away. Now, we have been notoriously unable to find planets that are smaller than Jupiter for a long time. Now, we've gotten better at it, but machine learning allows us to find even more. So, whereas we now have 3,600 planets that we know are confirmed, that number could skyrocket. Now, we already know that there's more planets in the universe than stars. You go to the darkest part of the world and look at the vast multitude of stars over your head, and you will find that there are more planets than all those stars you can see. And that's pretty cool. Now, the star that is Kepler 80, it's actually a M, all right, M0. That is, there's 9, ranking 0, 1 through 9. In each letter designation for the spectral type, all right, or the spectral class. And this spectral class is M, and that spectral classes of O, B, A, F, G, K, M. M is at the end. What's that mean? It means the lowest temperature. So this star is a very low temperature star. Now, I don't mean 25 degrees. I mean it's about 2,500 degrees Kelvin, right? And the Kelvin temperature scale is something you can look up. It's easy. It just gives us a way to say 0 is the lowest it can be. Absolute 0 is 0 degrees Kelvin, okay? And that's minus 273 degrees Celsius. So 0 is the lowest, and this star is about 2,500 degrees Kelvin. Now, it's fusing its hydrogen into helium in the normal way that stars work, okay? But the thing about this is the machine learning techniques actually discovered that the planets are actually in resonance. Now, what does that mean? Well, it means that they all orbit the star and return to the same place in their orbit in the exact same way every time. So that if the first planet comes around and stops at this particular place on the compass, setting or compass, angle, the next planet will be at say 40 degrees ahead of it. And every time these planets go around, that same thing happens every time. Now, that means that's significant, okay, because that tells us something else. Now, it takes about a day for the closest planet to circle the star. What's that mean? It means that's its year, okay? Ours is 365 days. Its year is 1 day. I mean, that's a short year, let me tell you. And the farthest one takes 14 and a half days to go around the star. So that's its year. So now the thing is, the star is so much less powerful than our sun, all right, that the habitable zone, that zone around which a planet could survive and live within just fine, is basically just an area that's a little narrow band where water might exist on the surface. And that distance is still only about 1/3 of the distance to Mercury, okay, from the sun. So it's really a very small band in a very narrow place, but that's where it is. So the star is really just a mere percentage, a small percent of the sun's total output. It's an incredible star, and it might be what we call an ultra cool dwarf, and it's really ultra cool in a lot of ways, but ultra cool in temperature too. Now we probably think that there's no real habitable planets here, okay? Now that's sad, okay, but I will say this: these planets are all way too close to the star, all right? And the habitable zone for this star is farther out than any of the planets that we have found so far are in. So there's none that are going to be in that habitable zone. So why did I bring it up? Why is it in here? Well, it's in this list because these were found by artificial intelligence, machine learning techniques. And this is just a preview of what we're going to see in the future. And so that's pretty cool. So now, before we move on to Kepler 452, Kepler 452 is the next star we're going to talk about, and that's the one that I think we're going to really, really like to hear about. But I want to just, come in and check on some questions. Now, Ronald asks, are there sound waves in space, and do these exoplanets have any sound signatures? Well, sound requires a medium through which to move, and you know this when you're at an air show and a jet goes by and you feel the rumble and it hits you in the chest and you feel that. That's air pressure hitting you in the chest. That's what sound is. Sound is a phenomenon that is actually transmitted through compression of air, all right? And so there wouldn't be any sound waves in space, no. But on an exoplanet, there would be. We'd have to get into the atmosphere of an exoplanet to hear the sound signature. So that's pretty cool. Anyway, now there's another one. Daryl asked, and of course, Daryl's a great guy. He actually asked some really good questions, and he's a good friend. And I'll tell you this: he asked a question about what happens if the transit, that is, the star having its orbital plane in such a way that the planets, when they go in front of the star, we can actually see it from the Earth. Well, that orbital plane might not be directly in line with the Earth. And if it's not, we may never see a transit, okay? So we might find stars that could have planets around them, but we'd never know because we'd never see their light get diminished the tiniest bit as a planet passes in front of it, but as from our point of view. So we know about that, and we know that there are techniques to determine whether there might be a planet. All right. Some of these techniques are gravitational lensing, where you might actually see one of the planets circling the star by the effect it causes from its gravity on a more distant star. And as the more distant star is passed by the planet going around the star, the planet we cannot see because the angle of its orbit's not, in line with ours, not with our sun, it might warp the star a little bit and cause what's called a gravitational effect or a gravitational lens. If it does that, we can see that, and that would help us confirm it's a planet. Another way is to measure something called, the star's position in the sky, and this is the one that's most fraught with error. But if you can actually measure that the star changes positions in a rhythmic manner, then you're measuring something that's causing the star to wobble. And if that star wobble is not caused by a white dwarf that's not quite visible, or the white dwarf star, or by a heavier planet that you can't see, you have to figure out what's causing it to wobble. And if it's not your machine error that's causing it, which can happen, then it brings up the question of whether it's a planet that's causing it. And that's something else that has been a plague for astronomers for a long, long time, okay? But there's still yet other ways. The orbit may not be aligned perfectly, and we might not see transits, but a star might be doing a wobble where we can actually measure what's called the Doppler shift of the light. All right, as the light comes toward us, the star's light will be moved a little bit toward the blue end of its spectrum. Right, and as it goes away from us, we might see it get moved toward the red end of the spectrum. That's the Doppler shift. In the same way that sound, which is only just used as an example here, the sound of a train whistle coming towards you goes when it goes by, or a car horn, right? That's Doppler shift of sound. Well, the sound waves are more compressed as they approach you, and then they're lengthened out as they go away from you. So it corresponds to high pitch, low pitch. With light, it corresponds to high energy, low energy. So high energy blue light to low energy red light. So we actually see that happen with light. And that could be how we can determine that the planets are there. But we can't catch them all, especially at some distance. So that's something we have to consider. So let's talk about Kepler 452. Now, there's only one planet in this system, and it's called 452b. It's 1,400 light years from the planet, and it circles a star in 385 days at 1.02 astronomical units. Hey, that sounds kind of like us. Slightly longer in a year. The star, believe it or not, is a G25. That is exactly what our sun is. Now, the sun has a certain amount of output of energy that it has. This star is just 20% brighter than our sun. It's also 6 billion years old, which is 1.4 billion years older than our sun. Now, what does that mean? It means that if there was a civilization that could have formed on this one star's planet, that it might have an extra billion years plus to develop. That's pretty cool. And going back to the question in chat, if there was a moon around this planet, then there might be tidal pools formed that would aid in the learning, basically the mutations that led to lungs for breathing air, if the air is, if there's even air on the planet. So you see, that's very interesting to me. And 452b here at Kepler 452, it gets 10% more sunlight than the Earth gets. Now, the star is older than ours, so it was probably just a little bit warmer now than it was when it was younger. All right. The star, as it ages, the light will tend to get hotter on the planet as the star changes evolutionarily. And this is before the star dies eventually. The star might go to like 10 or 12 billion years before it dies. So, but as that happens, it's going to age, to that age point, and then it's going to start to get a little bit warmer as the processes change within it. Now, that's something that is very interesting too, because if there's a civilization here, they had, like I said, 1.4 billion more years to develop, and now that's incredible to us. Now, 452b has been termed Earth 2 or Earth's twin. It is probably the closest planet to an Earth-like planet that we have yet found. So from the year to the location in its habitable zone, and it's slightly larger than the Earth. All right, now this is interesting. Now, we don't actually know the mass of this planet, all right, but we do know its radius. We've been able to figure that out because you can tell where the light first starts to dim at the star, and then where that curve bottoms out, all right, means that the planet's fully being, fully transiting the disk of the star. And then as it begins to, come back up, the light curve begins to come back up and then come off, we can measure the width of that. And knowing its orbital speed, we can actually figure out how big the planet is, all right? Now, the radius is 1.6 times our Earth's radius. Now, that means that the gravity on this planet is going to be 1.7 times the Earth's. Now, here's one for you. What would alien life look like on that planet? Let's suppose there's an oxygen atmosphere, beings like us. The universe basically has created a template for the Earth. Basically, if you look at every life form on the Earth, they all have, 2 legs or, 4 legs or 2 arms, okay, and 2 legs. I mean, they're bilaterally symmetric across their center line on the outside to interact with their environment. Everything has to do with symmetry on this planet. There's no, as I said before, there's no pogo stick cows bouncing around, moo, 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 So that said, we don't have that kind of thing. We have symmetry here that is a big, big template, I think, in the universe. What would have happened elsewhere? So if there's another life form out there that has developed, okay, then they've had this extra time. So let's say they look like us. What does that mean? Now we have to take the benefits and we look at the detriments now. Let's play devil's advocate here. There's no additional planets apparently, but that could change. Okay, machine learning techniques could find a lot more. We don't know. That's coming. But let's suppose there's only 452b, that one planet. It means that there's no outer planets to sweep deadly comets and asteroids away from the main planet. That'll be a target. Jupiter acts as a vacuum cleaner to clean out, the solar system of debris. If you recall, Comet Shoemaker-Levy, hit Jupiter, and you saw these big black impact scars on Jupiter for weeks. Now, where would those impact scars go? They'd go on the planet, perhaps, if it didn't hit the sun. It's a big gravity well. It's either the sun, their star, or the planet. So, it's probably a good chance the planet might get hit too. So, if there's no moon, then that means there's no tides, all right? And the only tides you would have would be the tides caused by the star itself. We have tides from the star. If we didn't have a moon, we'd still have tides. But guess what? It means that life might have evolved a little longer through the process to get out of the water, because the tidal pools would have been much smaller. All right. The sun is 400 times further away than the moon, so the gravity is that much more reduced as felt by the Earth. The moon is much closer, so we get relatively radical tides here on planet Earth. So, without the moon causing tides around that planet, well, we might get a different evolution of life there. Now, that means, well, maybe life would still evolve, but it would take a little longer. Well, guess what? They've had a little longer. They've been, they've had, 6 billion years, and maybe that was enough, don't you think? I mean, it's possible. This star, as I said, 1.4 billion years older than our sun. So they've had that, extra time. So maybe they actually could develop. Maybe they did. And it would only take a few 100 million years of development as a civilization like ours for them to become a super civilization and be interstellar. Okay, now, let's say they did come here. They would truly be like supermen and superwomen. All right? They existed under a much higher gravity, 1.7 times the gravity. And they would go interstellar not with generation ships that would take them thousands of years to get here, but they would use string theory or possibly the Alcubierre drive to make their trips. And so they would actually come here in a relatively short time. Their muscles will have been conditioned to higher gravity evolutionarily. All right. Now, it's not quite the same, but look how strong we appear when we're on the moon, which has 1/6 the gravity of our planet. All right. Now we have to wear big bulky suits, so it's a little clumsy and awkward. But just imagine if we had a really finely made spacesuit where we had all the flexibility of a normal body on the moon. We could do somersaults and jumps, high jumps. We could probably do incredible things. On the moon, we could jump 6 times higher from a standing position, roughly, than we could here on the planet Earth. All right, for the weight we're carrying. So 6 times, off the weight. So that is something that's pretty cool. And if they're here and they have existed in a much higher gravity, 1.7 times ours, okay, then they would probably have very powerful legs and arms as opposed to us. They would be, again, super people. It'd probably be like true, superheroes, if you want to say it. They would end up being the true superheroes. And I think that's a pretty cool thing. So the last star that we want to talk about right here is Gliese 667. That's Gliese, Gliese. The Gliese star catalog is one that I actually grew up with. In part of my degree, I analyzed Gliese stars. And the Gliese 667 is a triple star system. What's fascinating about this triple star system is that this star system is really interesting because you can compare it to Alpha Centauri in a way. All right. The stars, the 2 main stars are capital A and capital B. And we designate stars with capital letters. And those are K-type stars from the O, B, A, F, G, K, M. Now, the Alpha Centauri stars are G-type stars, so one spectral class before. But there's a C-type star also in this system. So we have capital A, capital B, and capital C. And it's a red dwarf, just like Proxima Centauri around capital A and capital B Centauri. And the capital C Centauri is Proxima, which is a red dwarf. So it's kind of a mimic of the Alpha Centauri system. And that's really cool. But check this out. This is something that Alpha Centauri is not, as far as we know. All the planets there are super Earths. They're bigger than the Earth, but they're all most likely rocky planets like Earth. All right. You know, one has a 1.8 times the Earth radius, and its year is 28 days. Another one has a radius that's 1.5 times ours, and its year is 39 days. Another one has the same thing, 1.5 times the Earth radius, and its year is 62 days. But that's not the most important thing. The most important thing is that all three of these planets are in the habitable zone of the star. That's fascinating, because now that means that there could be a civilization that might have gotten a jump start on planetary travel, because unlike Venus, which is farther away from us than these planets are from each other, unlike Venus, these guys can go to the star or go to the planets that are elsewhere in their solar system, and they'll be habitable potentially. That's a great thing. We don't have that capability, all right? You know, this one has the most interesting possibilities, this system, and that's why we bring it up. So, of all the systems, okay, that we're mentioning here, this is the one that I think we can focus on as a really cool one. That 452 is a really good one too, because of its very close similarities to the Earth. But so far, we only know one planet there. We need more, I think, for a planet to be fully habitable. Now we ask, could intelligent life have evolved on any one of these planets? Perhaps it exists on all three in various states of evolution. Started independently on all three. Isn't that something? It could be. Or perhaps life arose on one and they colonized the other two. Or there's life on one and the other two are still to be colonized because they're not that far in their evolution yet. You know, our system has no convenient colonization targets. We all talk about colonizing Mars and even the moon. But the moon is airless. These planets could possibly have atmospheres, and they're all pretty much the same size. And that's something that, you know, any type of alien civilization moving from one planet to another, that'll be a benefit to them. So I view this system as sort of a jumpstart system for any system that's trying to look at colonization leading to eventual interstellar capabilities. And that's something that I think we want to I think that's something we want to consider. And I want to also, you know, say that, you know, we could have three big planetary societies here all in one system. But now, let's consider the star, all right? I said it's a red dwarf, all right? The star is 1.4% the brightness of our sun, and it will probably last trillions of years to our billions, okay? Because stars that size and that temperature, they're just little percolators. They sit out there doing their thing for trillions of years. So life forms would have plenty of time to develop once the star is past its flare stage. M stars are also known to, you know, throw off a lot of ultraviolet flares throughout their lifetime. But again, if life develops, if it's conducive to life, then life will probably find a way, as Jeff Goldblum says in Jurassic Park, as Ian Malcolm, the scientist, life will find a way to actually overcome that. Because he speaks as an actor, he says that line from the movie, but actually it's spoken out of truth in science. We see that life finds ways here. Okay, life found a way to exist at the bottom of the deepest part of the ocean. Life finds a way to exist in the hottest pools of alkaline, you know, chemistry here on the planet. So it's really fun to speculate about this stuff, you know. Now, maybe only two of the planets around the star are habitable, all right, and the closest one being scorched with the ultraviolet radiation. I mean, but hey, we don't know. Now, James Webb will make this a target, and we'll probably find out more about the system. And I'll tell you, I really think, and I said this on Commander Cobra Show just a few minutes ago, a little while ago, I think we're going to discover that we have a most incredible year coming up. We're probably going to find a tremendous amount of planets that are habitable and planets that are like the Earth. You know. Now, I just want to say real fast, we have a lot of dedicated KGRA listeners, and I just want to give a shout out real quick to Jude, to Daryl, Maggie, Ron, Jennifer, Dan, Keith, Rebecca, Chuck, Jana, Roxana, Kathy, Paul, Vicky, Lorraine, Charles, Andy, Heidi, Bill, Karen, Marianne, Alejandro, Stacy, and thousands more. I want to thank you for making SkyTour Radio what it is. Now, we have to go, but we'll be back next week. But until then, keep looking up, except when you're driving. All right? So good night. On behalf of Amanda and I, we had a great time with you tonight. See you later.